Okay, so far we've been thinking of um, functions of two variables as graphs of surfaces in three-dimensional space. But I wanted to show you a couple examples of how this occurs in a biological setting. And these examples are what the book uses too. The two big examples are body mass index and which is also known as BMI. And that's a very common measurement that's one indicator of a person's health. Um, and how it's defined is you take a person's mass in kilograms, so it's in metric, divide by their height in meters squared, and it gives you a number, okay? And that number, depending on what the number is, kind of gives you a measurement of the ratio of the person's mass divided by the square of their height. Which could indicate their fitness level. So for example, if you had a person who was 5'9", which is about 1.75 meters, and weighs 155 pounds, which is about 70 kilograms, their BMI, if you plug that into this formula, would be 70 over 1.75 squared, is about 22.9. And we were talking about level curves, and if you look at the level curves for the BMI function, remember how we do that is we set our function f of xy normally, in this case b, which is a function of your mass and your height, equal to a random value k. We used to think of that as z. We have k equals m over h squared. And if we just by choice solve it for h, manipulate it, you would get h is equal to the square root of m over k. And so we could plot some level curves for this, picking different values of k. And what you would see then is a bunch of curves that look like the square root graph. And the larger k is, okay, that's going to make the output a little bit smaller. So your square root graph is going to get a little bit lower for higher values of k. And this BMI chart is very common. You could search this online and you'll see a graph that looks very similar to this. And they'll even break it down. So somebody has decided that if your BMI is under 18.5, then you're considered underweight. If your BMI is between 18.5 and 25, that's considered normal. Between 25 and 30 is overweight, and over 30 is obese. So yeah, and this is a very common chart. Some of you may already be aware of it, but if not, you should look up body mass index chart, and you'll see a graph that looks very much like this. Okay, another example of a function of two variables is an infectious disease model, which is something is very much on our minds these days. And in fact, one number, if you've been watching the news or listening to the radio, that you've probably heard a lot of is called R naught. R sub 0 is read as R naught. And it's a very important number in the science of epidemiology. Public health officials, when they want to quantify how infectious or contagious a disease is, the common measurement is to find the R naught number. And R naught is defined to be the average number of new infections that an infected individual causes when introduced to a completely susceptible population. So to give you some perspective, the R naught number for the COVID-19 virus, which is at this moment very prevalent in this country and all over the world, is estimated to be between 1.5 and 3.5. So what that means, let's say the R naught value is 3. What that means is if the R naught value is 3, then somebody who has the virus is expected to infect 3 other people. So you can imagine how quickly a disease would grow if each person who has the virus is infecting 3 other people. That causes tremendous growth of the disease. And even to put that in perspective, I looked this up. The R naught value for measles, which many, many years ago was a terrifying disease for kids. Well, everybody, but it mainly affected kids. The R naught value for measles was between 12 to 18, which is really high. That was a very, very contagious disease. Nowadays, we have vaccinations that keep that particular disease under control. Anyhow, so one model for R naught is given by this. So it's a function of 2 variables. It's a function of the number of days, the average number of days an infected individual remains in the population while infectious, and the vaccination rate of the population. So this model, 5 times 1 minus v times d over 1 plus d, is a particular model that the book uses. Again, going back to the COVID-19 virus right now, what's one troubling thing about that is nobody is vaccinated right now. The value of v would be 0 now. So you can see if that's 0, then we're not making this term any smaller there, right? Also of note, what is one strategy that we are currently using to fight this virus is to keep people indoors, right? To shelter in place, try to stay within your own home or within your own family. And why is that important? That affects the number of days you're out in the population. The more days you're out in the general population, that's going to have an effect on the R naught number because that increases the chances that you are going to infect somebody else. So anyhow, it's a very timely, I guess, model to be looking at right now. So based on all of that, ideally, you would want a low number for R naught. The magic number is 1. Once the R naught value dips below 1, that means the average person is infecting less than 1 person, which would then obviously cause the virus or the disease to decrease in size. So what conditions for V and D will make R naught approach 0? There's a couple of questions we could ask about this. Well, if you look at the equation, if the vaccination rate were to approach 1, which really means 100% vaccination rate, well, look at the model. What would happen if V approaches 1? This term goes to 0 and your R naught would approach 0. If everybody gets vaccinated for the disease, then the disease will not spread. What's another thing that can affect R naught or cause that to decrease to 0? The number of days, right? If possible, if somebody becomes infected with the disease, if they immediately quarantine themselves, something that you've been hearing a lot about, meaning your days out in the general public once you have the disease, if you can make that equal to 0, look what happens to the equation. If D is 0, this part becomes 0. And then I guess in theory, it wouldn't matter about the vaccination rate. R naught would have to approach 0 as well. These two models, the body mass index, the BMI, and the infectious disease model, you're going to see the book comes back to this over and over again. So these two models you're going to want to be familiar with. We're going to work with them again. Okay.